Swayam Prabha. Digital India. Educated India.
So in the last lecture, we were trying to understand, what various modes of addition to a carbonyl compound were. And, we looked at, for example, enantiotopic phases and how we name them and how they are quite precise in describing the mode of attack and so on. Okay. So the important point to note there in the previous lecture was that when you had, a chiral center, so you also have not just enantiotopic phases, but you also have diastereotopic phases. And so the important point that when the carbonyl group was quite far away from the chiral center, there was really literally no effect of addition. That means you got a 1:1 mixture of the two products that could be formed due to two possible modes of attack. Whereas when the chiral center was close enough to the compound, that is when you had the example that we looked at was this, right? When you have this compound and you do a LAH reduction, you ended up with a 3:1 mixture. Okay, so in order to understand this, I'm going to now provide you a theoretical framework that helps us reason this out. Okay, so a lot of things in chemistry are actually first observed experimentally, and then a theoretical framework is developed. Okay, so now in order to understand this, let's go back and look at another example of something that we have already studied, which is elimination reactions. Okay, so in E2 elimination reactions, we have encountered the situation where this elimination occurs with an anti-periplanar transition state. Okay, so anti-periplanar configuration or anti-periplanar geometry is in place. Okay, so what this means is that you have the leaving group here and hydrogen over here, and the other groups are in this kind of orientation. And what happens is that this bond starts to break, and you have a new double bond that is being formed, and this bond starts to break. Okay, so you have this kind of an arrangement, and of course, just to be complete, the base is attacking here, and then you have the formation of the double bond and the leaving group leaving. Okay, so what this anti-periplanar means is that when you draw a plane that encompasses or that has this, and this, they're all in the same plane. Okay, so this is what we mean by anti-periplanar relationship. Okay, so this is something that you have already studied previously. Now, when I want to use this information for explaining the distribution of products, then what I would need to do is I'm just going to take an example that helps you sort of reason this out. Okay, so the example here is the following. Okay, so when we start with this particular alkyl halide, so you have hydrogen here and hydrogen phenyl. Okay, and there's another hydrogen here and there's a phenyl here. Okay, so this is basically an elimination reaction that happens in the presence of a base to give you styrene. Okay, so let's now look at this elimination from this configuration or conformer, and it attacks here, and now this is lost and chloride is eliminated, and you get the following product. Okay, so the following product is basically, the way we draw out the product is this phenyl ring and this phenyl ring are actually on the same plane. So you would end up with the following cis isomer or Z isomer. Okay, now I can always do some rotation of this bond, and if I do the rotation of the bond, then we'll keep this carbon to be constant and we actually rotate this carbon over here. Okay, so now if I do that, let me just draw this out the way it is drawn. So we have phenyl, hydrogen, Cl, and this is the carbon-carbon bond. And now when I do the rotation, I'm going to move this hydrogen further down, and the phenyl ring is going to be over here. Okay, so this hydrogen goes here and this hydrogen goes here. Okay, so at this conformation, and you will notice that this is just a carbon-carbon bond rotation, and so there's nothing magical in this. It can happen very nicely at room temperature. Okay, so now if a base attacks, right, in this particular conformation, you still can undergo elimination. The only thing is that it's going to give you the E product. Okay, so just to recap, we're just taking this starting material and we're treating it with a non-nucleophilic base, maybe potassium tertiary butoxide or something like that, and we're just looking at the products that could be formed. Okay, so from this conformation, if we start from this conformation, we end up with a Z or Z isomer, and if we start with this compound, we end up with the E product. Okay, so now one would be very tempted to say that this conformation is more stable and therefore the population of this conformation is higher and it would give the E product. Okay, because we know that the E product is going to be the major product of this reaction. Okay, so I'll repeat. It is very tempting for us to say that the E product is formed, which is formed from this conformation. This conformation is going to have a higher population when compared with this conformation. Okay, so that kind of an explanation would certainly help us reason out or help us rationalize the result. Okay, however, what is important here is that the barrier for conversion of this conformer, the conformer that is leading to the Z product or Z product, and the conformation that is leading to the E product, that barrier is extremely low. Okay, so now I'm just going to draw the two, I'm just going to draw an energy profile which describes this process. Okay, so this is the energy and this is the reaction coordinate, E and RC. Okay, so now this is the conformation, one of the conformations, and this is the other conformation. Okay, now let me just redraw this so that it's easy for us to understand this. I'm just going to draw it a little smaller. So here is the hydrogen phenyl ring. The Cl is here, the hydrogen is here, and phenyl is over here. Okay, so as you will see here, the two phenyl rings are actually quite far away from each other, and so that must give this conformation a little bit of higher stability compared to the other conformation. Okay, now let me just draw this a little further away so that we can draw the other conformation nicely out. So this is, let's say, the other conformation where the back carbon remains the same. So you have the phenyl ring, and then you have, sorry, let me just redraw this. It's a little difficult to read this handwriting. Just trying to put everything on this page so that we can have the complete figure. So this is the carbon, and this is the hydrogen, and this is the Cl. So this back carbon or the carbon on the right remains the same, but now in the other carbon, what we have is we have hydrogen, and this is also hydrogen, and this is the phenyl ring. Okay, so notice that I have put these two rings are close to each other, and therefore this is of a higher energy. This conformation would be of a higher energy compared to the other. Okay? Now, what we know from various experiments and theoretical calculations is that the barrier to conversion is actually not very large. So people have estimated this to be somewhere between 10 to 15 kilojoules per mole, which is easily accessible at room temperature. Okay, so even if you go to a slightly lower temperature, you might slow this down, but it's really something that is going to be happening very rapidly. So the argument that one would make, saying that this conformation is actually of a higher population, is not something that would hold good. So we have to now develop an argument or theoretical framework that helps us understand the outcome. Okay, so now going forward, I'm just going to call this as this is going to be the E conformer, and this is going to be the Z conformer. Okay, so let me just redraw this energy profile again. So just to recap, what we have agreed is that the difference between the Z or the Z conformer and the E conformer is real. That is, E conformer is definitely more stable, or the conformer that's leading to the E product is more stable, but this barrier is going to be so low that it's going to really freely interconvert. Okay, so now given this, now how are we going to explain the difference or explain any difference in the product formation? So the way we would do this is now to propose or suggest that the product that is going to be formed, which is the E product, E olefin, we already know that the E olefin is going to be more stable compared to the Z olefin. Okay, and how do we find that out? You may recall that if you do a hydrogenation reaction on the Z olefin and the E olefin, they're going to give you the same product, which is the alkane. And now if you measure the heat of hydrogenation, the E olefin actually liberates less energy, which means that it is more stable when compared to the Z olefin. Okay, so that's how we experimentally determine that the E olefin is more stable. Okay, you can also do it by combustion analysis. By measuring heat of combustion, you would get the same result. So there are several thermodynamic parameters which suggest that the E olefin is actually more stable. So therefore, now coming back to this picture, what we need to understand here is that the difference in the product distribution would be a reflection of the rate at which the product is going to be formed. So if E is the major product that is being formed, then the rate at which E is being formed is substantially higher than the rate at which the Z is being formed. Okay? So in order for the rate to be higher, what we can propose is that the transition state leading to the formation of the E product is lower in energy when compared to the transition state leading to the formation of the Z product. Okay, so given that the rates of formation of the E is substantially higher than the rates of formation of Z, this may be reasonable to propose. And now if I draw out an energy profile, what emerges is that you're going to have a transition state that is of lower energy when compared to the Z. Okay, so therefore what we can sort of understand from this is that the transition state of E, okay, has lower energy or is more stable compared to the transition state of Z, right? Or the way to understand this is that the barrier to the formation of E is substantially lower than the barrier to the formation of the Z product. Okay, so this is something that we may want to sort of look at again. So I'm just going to repeat this part a little bit so that we can understand this a little better. So when we consider reactions where there's going to be a competition. Okay, so here is a competition between the formation of the Z product and the E product. So we know that the Z is the minor product and the E is the major product. Okay, so what we tempted to do is to say that the conformation that leads to the formation of the E product is substantially higher in population compared to the conformation that is leading to the Z product. Okay, but that is not really going to help us explain the result because this barrier is extremely low. Okay, so like we discussed, it's about 10 to 12 kilojoules per mole, and that's easily accessible at room temperature. So what may be more likely is that the transition state or the barrier to the formation of the E product is lower than the barrier that is encountered to form the Z product. So this difference, that is the delta G double dagger or delta of EA, activation energy, is something that's going to play a role in determining the product ratio in the reaction of interest. Okay, so this principle is known as the Curtin-Hammett principle. I'm just going to redraw it over here. So the Curtin-Hammett principle basically says that when you have a reaction with multiple conformations in play, the more reactive conformation is going to produce the major product. Okay, so that means that the more reactive conformation, which is the E conformation, which is going to give E, is more reactive than the conformation that is going to give you the Z product, and therefore you get the E product as the major product. Okay, so this helps us develop the framework to understand the difference in the carbonyl chemistry example that we looked at. So I'm just going to summarize this by drawing some rate constants over here. So when you have the conformation 1 in equilibrium with conformation 2, okay, and conformation 2 gives you the major product, and conformation 1 gives you the minor product. Now we can describe each of these processes using rate constants. So let's call this as K1, K minus 1, which is the reverse of the C2 going to form C1, and let's call this as K major, and this is called the K minor. Okay, so what we can understand from this is that K1 and K minus 1, okay, are actually much faster compared to K major or K minor. Okay, so this is or and not divided by. Okay, so therefore what is important is that this conformation interconverting from here to here is going to be a really fast process, right? And so the product distribution is actually dictated by the value of K major, which is going to be higher the value, the more of the major product that's going to be formed. Okay, so with this background, now we need to start looking at the formation of the two products when we add lithium aluminum hydride to that carbonyl compound. Okay, so now we understood that based on the Curtin-Hammett principle that differences in major and minor products is likely due to differences in reactivity between conformers. And so therefore in the carbonyl example that we are looking at, so there might be two states A and B, okay, and one of them may be more reactive and the other one might be less reactive. Okay, so therefore what we need to now understand is to figure out how we can reason this out, these differences in the reactivity. Okay, I mean there are probably multiple conformations that can exist, but our interest is in trying to understand two of these because we learn very soon that the addition is going to happen through one side or the other. And so in order to understand this, the question that we have to ask is, which of these is more reactive? Okay. So, like we mentioned earlier, we don't really care about the population of this conformation because they're just going to be quite rapidly interconverting. Okay. So, before we go forward with understanding the stability, let's understand some stereochemistry or how to represent molecules. So, let's start with acetaldehyde, CH3 C double bond O H. Okay. And so, if I look at it from here, so these are my eyes and I look at it from here, then it's going to look something like this. Okay, so the C double bond O is over here, hydrogen is over here, and the CH3 is here. Okay, and if I have to draw this in the form of a Newman projection, and if I look at it from the side that I have drawn, so I have the back carbon is with CH3, the front carbon is C double bond O, and then there's a hydrogen, and the back carbon has CH3. Okay, so this could be one conformation. Now, if I do a rotation, we're going to get another conformation, which is the C double bond O is here again in the front, and maybe this time the hydrogen is going to be here, here, here. Okay, so you can, in your free time, you can practice the various rotations around this carbon-carbon bond. So just to repeat, so this is the carbon-carbon bond, and if we look at it from here, this is the front. The front carbon is C double bond O H, which I'm showing over here, and then the back carbon is the CH3, which is shown here. Okay, so this, you need to start getting familiar with this kind of notation. Now let's take another example. We can take an example of maybe acetophenone, so that we can draw a little bit more complicated molecule over here. Okay, so acetophenone is over here. Now if I'm going to look at it from this side over here, then the way this molecule is going to look like is there are two hydrogens sitting here, and so the way this is going to look like is, this is the carbon that I'm using to draw the back carbon, and C double bond O is here, pH is below, and now you have possibility of the two hydrogens, which can be, two hydrogens are here, and the CH3 is actually behind. Okay, so if I have to draw this molecule using this Newman projection method, it's going to look like this. Okay, and now you can always do rotations, draw out other conformations. So you have C double bond O, pH. Now your CH3 can be perpendicular to the carbonyl, and so this is 90 degrees over here, and so this can be perpendicular to the carbonyl, it can be eclipsing. You can draw multiple conformations that are relevant to the carbonyl chemistry. Okay, now with this background in mind, let's now look at one of the examples that we want to understand. So let me just draw out this particular molecule, and then we can have a discussion about it. So one of the methyl groups is here, hydrogen is here, and it is an aldehyde, C double bond O H. Okay, so now what I want to do is I want to draw this looking at it from this direction. So I have a C double bond O H. Okay, and now I'm just going to be careful and actually label this in different colors. So this hydrogen is going to be in yellow, and this methyl is going to be in blue. Now if I have to draw this out, if I'm looking at it from here, the hydrogen is on my right, and the methyl is on my left, and the phenyl ring is actually eclipsing the carbonyl compound. Okay, so this is how I would draw this. Now let me take another example where I am just going to do a simple swapping of the methyl and hydrogen so that we get some practice. So the methyl is over here, hydrogen is over here, and phenyl ring is here. So the way this conformation is drawn is that the C double bond O is up, H is here, the phenyl ring, as you can see, remains over here, and the green hydrogen and the purple methyl group are going to be important. And so when I look at it from here, obviously the phenyl ring is eclipsing, but now the methyl group is on the right and the hydrogen is on the left. Okay, so this is something that you need to start getting familiar with in terms of drawing conformations. All right, now let's try to see if we can draw this in a slightly better way. Okay, I'm just going to spend a little bit of time and draw all the conformations, and so you need to be a little patient with me here. So let me first draw one conformation of this molecule, C double bond O, H. Okay, and let's say I'm just going to draw one of the conformations where phenyl is here, hydrogen is here, and methyl is here. Okay, now what I'm going to do is I'm just going to do a rotation. This phenyl ring moves down, and I'm going to draw another conformation like this. So the carbon remains intact. Okay, so the phenyl moves down, the methyl moves from here to here, and then the hydrogen is now perpendicular to the carbonyl. Okay, now I'm going to draw one more conformation where I am doing more rotation over here, and here the C double bond O is here, hydrogen is here, and now what I've done is, since the phenyl ring is moved here, the methyl now becomes perpendicular to the carbonyl and hydrogen is very close to the carbonyl. Okay, now let me draw one more conformation where we do one more rotation. Okay, so this time the phenyl ring is now perpendicular. Sorry, let me just draw out the C double bond O, H. The phenyl ring is perpendicular. The methyl is down. So remember that the methyl goes down here, and then the hydrogen moves up close to the carbonyl. Okay, we have a couple of more rotations to do before we get back to the original compound, and so let's do that. So this again, do one more round of rotation, and so here is a C double bond O, H. Okay, and now when we look at this, what we are going to do is, again, we're just going to rotate the phenyl ring in this clockwise direction. So when we do that, what we end up getting is the following conformation. Let me just erase this arrow a little bit so that I can squeeze in one more conformation over here. So here is the C double bond O, and when I do a rotation of the phenyl, then the phenyl ends up here, pH. Okay, and the hydrogen is now perpendicular to the carbonyl and methyl is over here. Okay, and the last conformation is with the phenyl ring moving further, doing one more round of rotation, and it's going to give you the C double bond O, H. Okay, and sort of phenyl ends up here, the hydrogen is over here, and methyl is now perpendicular. Okay, so I can draw out 6 important conformations, and just one more, just to be clear, if I just do one more round of rotation, I get from here to here. Okay, in this direction. So we have gone an entire circle. Okay, so in order to develop this model further, we need to understand that there are some conformations that are going to be important. Okay, and how do we understand these important conformations? We try to look at models that can help us with explaining the result. So as far as we are concerned, the important conformations are the ones wherein the largest group is perpendicular to the carbonyl. Okay, so the largest group being perpendicular to the carbonyl occurs in two of these conformations that we have looked at. So one is this, okay, and the other one is this. All right. All other conformations that we have looked at now do not have the largest group perpendicular to the carbonyl. So one important reason why we would want to sort of understand this is because these two conformations are perhaps are more relevant in developing the model further. Okay, so I'm just going to draw out these two conformations once again so that we understand this. So in the model that we are now constructing, we wish to consider the two conformations wherein the largest group is perpendicular to the carbonyl. Okay, so this is one of those conformations, and the other conformation is over here. Okay, so these are the two conformations that we are interested in.